at another group of organic derivatives called esters. And esters happen anytime an alcohol reacts with a carboxylic acid. Esters are a special kind of dehydration reaction. Dehydration reactions happen anytime we find a way to remove water. Take a look at the structure that we have here on the left. We have a 3-carbon chain, so originally propane, but the functional group makes this propanol. Below that, we see another structure with a 2-carbon chain. And this 2-carbon chain would have been ethane, but because of the hydroxide, this is ethanol. So we have propanoic acid with carboxylic acid and ethanol with the OH group. When we draw these close together, however, you see that the propanoic acid has an OH, so does the ethanol. If we can find a way to remove 2 hydrogens and an oxygen, it doesn't matter whether I take these 2 hydrogens and the oxygen off the alcohol or off of the acid. We find that we have essentially made water. This is the dehydration part. We've removed water. Well, what happens then? This oxygen no longer has a hydrogen attached to it. It has its 1 electron empty. It's like its hand is empty. This carbon no longer has an OH group, and so they join together. In an ester, we have a centrally bonded oxygen that connects 2 separate chains, and the side that came from the carboxylic acid will have the double bonded oxygen. Now, because esters are made from 2 separate compounds, we name both halves separately. In your mind, draw an imaginary line between that central oxygen. Name the side that has all the single bonds, the side that came from the alcohol, first. Name the side that has the double bond second. The first side is going to end with the ending YL, kind of like a branch. I know that's confusing, but again, they didn't invite us to the party where they made this decision. So we're kind of stuck with the rules. The second half is going to end in O8. So from the ethanol, we're going to have ethyl. Ethyl is what I name this half of the molecule. From the propanoic acid, we're changing it to propanoate. So all esters have first name, last name. Sometimes you'll find typists like to type the carboxylic acid and the alcohol as straight lines. They find it difficult to type all and format all of the different angles. COOH is still the functional group for my carboxylic acid. The letters you see in blue would more commonly be written like this. But again, that's difficult formatting for a typist. The ester sometimes has those central carbons written to look like this. You'd have the CH3CH2, and then in blue you'll see COO, CH2CH3. When you see typing like this, what I want you to remember is this first oxygen is our double bonded oxygen. The second one is the one that separated the 2 halves of the ester. You're going to get a chance to practice lots of questions on esters in your workbook on pages 50, 51, and 52. I'm going to do 1 or 2 examples with you from your workbook, though, on page 51. So if you'd like to work along with me, we'll get you a start on these. Question 1 on page 51 talks about ethyl methanoate. I can tell because of the 2 names and the O8 ending that this is an ester. Because I know it's an ester, I know that my ethyl and my methanoate will be separated by a central oxygen. The ethyl side will have 2 carbons, so I'll put 2 carbons. The methanoate side, methane, will have only 1 carbon, so I'll put 1 carbon on the other side. It doesn't matter if I put these to the left or to the right. Next, I look at the O8. The O8 tells me that this was the second half. It's the side that came from the acid, so it has a double bonded oxygen. That means this carbon needs a double bonded oxygen. Now, I'm going to draw it down because I didn't leave myself any room to draw it pointing up. It doesn't really matter. So I have created my central pivot oxygen, added the correct amount of carbons, and decided which side get the double bonded oxygen. At this point, I just add hydrogens to the carbons as needed. This first carbon has 1 bond and needs 3 hydrogens. The second carbon has 2 bonds and therefore needs 2 hydrogens. We don't add hydrogens to anyone but carbons, so the final carbon has 3 bonds already and requires only 1. This is the structure for ethyl methanoate. Let's take a look at the example immediately below that. When we look at the structure in question 2, I can see that my central oxygen that separates the 2 halves is right here. So the side with all the single bonds is the side that's going to end in YL. The side that has the double bonded oxygen is the side that's going to end in O8. We always name the single bonded side first. There are 2 carbons on this side, so we'll use eth for 2 carbons. So this was based on ethane. So ethanol or ethyl, both would be considered acceptable. The second half has 2 carbons, so again based on ethane, but here we're going to use the O8 ending. This is ethyl ethanoate. I will sometimes see it spelled ethanyl ethanoate, and that's considered acceptable for use in esters. Let's do one more example with you. The first question on page 52 asks us, what happens when we combine propanoic acid with 1-butanol? We're going to start by drawing these 2 structures. Propanoic acid has 3 carbons from the word propane. We put 3 carbons. I now have to add the oic acid group, which is an O and an OH. So here is the skeleton for propanoic acid. 1-butanol, butane, but means 4 carbons, so I'm going to make a 4-carbon chain. And I need an alcohol because OL. Now they say it's on carbon 1, and I know I can put carbon 1 on the left or the right, but experience has taught me that it makes it easier to put my 2 OH groups close together because I can see how to dehydrate or remove water at this point. So when propanoic acid and 1-butanol get together, the first thing I want to do is make water. I need 2 H's and an O. So I've got 2 H's here. I'm going to choose one of the oxygens, and it matters not which one you choose. But those 2 H's and that O react together to make H2O. This is water. What is left? Well, we still have these 3 carbons, with the third being attached to a double bonded O, and then this oxygen, who is now no longer attached to anything. This hydrogen, and this oxygen have now gone to form water. So this oxygen here will now attach itself to the 4 carbons that originally belonged to the 1-butanol. The name of the structure, again, this time we still have to name this side first. 4 carbons will be butyl, or butanol if you prefer. On the other half with the double bond, propane becomes propanoate. So we will make butyl propanoate in this reaction. So hopefully that gives you guys a good start to work on figuring out how to name and draw esters and how to figure out an esterification reaction.